In this case, we were told we want a single force, but we have to decide where along the system should we place this one force such that we don't need a couple in order to have this equivalent system. And my point A, my original system, I just copy everything exactly here. A 200-pound force 3 feet from A. A 100-pound force, again with that ratio triangle, 3 feet from the 200-pound force. And then 3 feet from that, we have this last 50-pound force, 30 degrees from the vertical. Our equivalent system is going to look a little bit different here. We don't have a couple, and we don't know where exactly yet we're placing this one force, but we know we want to put, we have an axis that we want to put it on. We want it to be placed along the axis of the object itself. So what we can do here is, since we don't know where on the axis it is, I'm just going to draw in kind of an arbitrary spot for right now. And I'm going to find out later through the moment equation what that distance should be. So I'm going to say it's some distance d from point A, which I'm going to find. And just like the last example, I'm going to break it down into its component form, the fx and the fy. And the goal here is we want to not have to put a couple into the system. So there's this fx, fy, and then a different unknown, the value of d, the distance the force is from point A. I could have also said that it was a distance d from the right-hand side, in which case I would get a different value from it. So I chose point A just because it was the most convenient in this case. I'm going to say it's a distance d from point A, but I could have measured it from any other point also. But it might have made the equations just a little bit tougher to find. So I'm measuring it from that extreme left-hand side. These parts are the same. I look at now my original system and find what's the net force in the x and the y. In picture number 1, in the x direction, I'll have none of the 200-pound force. I'll have 3/5 of the 100-pound force. Right, and it'll be 50 sine 30. So remember, we want to be careful with the angle measures here. Here the 30 degrees is given to us from the vertical axis. So the opposite to that is going to be the horizontal component. The vertical will be the adjacent. So don't always assume that cosine is associated with x and sine with y. I would say most often that is the case, but here is an example where it's not. So it's actually 50 sine 30, and that x component is pointing in the positive x direction, the y component in the positive y. So this will be plus 50 sine 30. Add these values together, and we get that the net force in the x direction is 85, and we're in pounds. In system 2, it's exactly the same as what we had last time. I only have that fx, and I know that it has to be equal to the sum of forces from system 1. Going back to system 1, in the y direction, I have all of that 200 pounds up in the y direction. I have, in this case, 4/5 of the 100 in the negative y direction. And now up, I have 50. This is now cosine 30 degrees. Again, for the 50, I need to use the adjacent leg to the 30 because that's going to be the vertical, and it's pointing up. Adding those values together, I should get 163 pounds. Then the easy part is looking at system number 2, Fy, 163 pounds then. I know Fx, I know Fy. What I don't know is, again, where should I be putting this one force? What's the distance I'm selecting to measure it from point A here? I can get that the third unknown using the third equation, the moment equation, where again I have a choice of where to take the moment about. Really, based on how I drew the distance here, I'm going to be best off taking the moment around point A. It's going to be more confusing if I tried to take the moment around, if I call that point B, because this distance is now going to be more complicated to measure. It would be 9 minus D. If I take the moment around A, then the distance this force is from A is always the value of D. So based on that drawing, I'm going to again select point A, but I could use any point I wanted. System 1, what is going to contribute to the moment around point A? Right, so the 200 pounds is 3 feet from point A, and it's positive because that is going to create a counterclockwise moment or twisting around point A. So that is positive. The vertical component of the 100 times 6 feet away, and that is positive or negative? That one is negative, it's clockwise. What about the 3/5 times 100? Right, so again, if we draw the components of this, the vertical component, oops, I'll draw it at that same point. Vertical component does have a horizontal distance or a perpendicular distance from A. However, the horizontal component has its line of action pass through A, so it does not need to be in this equation because its distance is 0. So just the vertical component of the 4/5, and then what else is going to be on the right-hand side of my equation? The vertical component of the 50-pound force, the 50 cosine 30. That's the amount of the force. And right, that is 9 feet away from point A. And, I already drew it. That is going to create a counterclockwise moment around A, so it is also positive. And just like we saw for the 100-pound force, the horizontal component of that 50-pound force has its line of action pass through A, so I don't need to include it here because the distance is 0, so it would just drop out. I get the net moment then around A for system 1, 510 pound-feet. Now in system 2, just a little bit more, or a little bit different than we saw in the last problem, what is the moment around point A in picture number 2? This is where the way we draw this is crucial here. It turns out not to matter. Let's imagine Fy turned out to be a negative number, negative 50. These equations we write are always based on the pictures we draw, not based on the numbers that we get. We always need to be consistent to the picture. According to the picture, the moment around A is positive Fy times D. If it turned out Fy was negative, after we write this, then we fill in the values. And if Fy is negative, then so be it. But this originally is based on the picture. So positive Fy times D. And again, we know from this equation that Fy is positive 163. And we also know that this net moment around A has to be the same as the net moment around A in system 1, the positive 510. Now from this equation, the only thing we don't know is the value of D. How far should this force be placed from point A? And we can solve that by dividing through by 163. 3.13, and this is in feet, right? Because this is in pound-feet. The 163 was in pounds, so this is going to be in feet.